Hey, this is Lab Group 806-5, and this is our MEC 2960 report on Flexure. In this lab, we studied beam bending using a strain gauge at the centroid of our sample. Our goal was to calculate Young's modulus through flexural loading and compare it to known material data. We used both theoretical and experimental methods to evaluate the stiffness and validate our results. Just as a quick background, what is three-point beam bending? Three-point beam bending is a type of flexural test we use in material science to measure properties such as the modulus of elasticity, flexural stress, and flexural strain. To be able to extract values from our experiment, we must first prepare our sample. After being given a piece of polycarbonate acrylic, we must find the centroid of the sample and attach a strain gauge which we are also given, making sure the flush side lays down onto the sample. Then strip and fray the wires on the tail end of the gauge so we can connect it to the multimeter. This multimeter will produce voltages which we can use to calculate our desired values such as strain during bending. After completing our sample, two different experiments can be conducted to find our desired values, such as strain and Young's modulus. First is the foam test, where we collect the V-rest values before bending our sample over the semicircle 3 different times with the strain gauge facing up. We took the average of each V strain to get our V out value. In the three-point bending test on the right, we place the sample into the vise with the strain gauge facing down. Have the fixture on the tensile machine just touch the sample, zero all gauges, and then begin bending the sample while recording on a phone where we can see the change in all three measurement devices, the force gauge, the displacement gauge, and the multimeter.
In the foam test, voltage from the strain was measured 3 times as it was bent around a foam semicircle, and was used to calculate the strain again, which was compared to the theoretical strain found from the radius of the foam circle itself. In the 3-point test, force, displacement, voltage, stress, and strain were measured across 20 points in time, and the slope was found using a linear trend line. Excel graphs were created to show the stiffness and strain of the sample under loading and the resulting bending. After measuring the V strained 3 times, the average was calculated and turned into V out by subtracting with the V rest. The V out, V in, and gauge factor could then be used to find the microstrain. The microstrain is 10 to the power of 6 times larger than the strain and was promptly turned into strain. Compared to the theoretical strain, the calculated strain only has a percent error of 16.34%, which is well within the expected range. Now for the 3-point bend test data. You can see the initial force displacement graph is quite linear, closely matching the trend line. The displacement-based Young modulus is found with the slope of the trend line times the gauge length cubed over the moment of inertia times 48. The stress strain graph tells a similar story to the force displacement graph, closely following the trend line. Unlike the force displacement graph, the strain-based Young modulus is easy to find as it's simply the slope of the graph. This graph represents the deformed beam at 12 pounds of force. It was taken by splitting half the gauge length into 50 points and calculating the displacement from its unbent state, then mirroring the second half to create the complete deformed beam. The Young's modulus from displacement is 436,873.773, and the Young's modulus from the stress strain graph is 444,819, very similar numbers, while the actual Young modulus of the sample is 333,586.797, which is somewhat off. However, the gap between all these values is well within the acceptable range.
So for our discussion for experimental data, we were able to verify our elastic behavior as our tables showed a linear relationship of our force versus displacement and our stress and strain, which confirmed elasticity during testing. This showed the accuracy of our measured elastic modulus of polycarbonate acrylic, which was our material sample that we were giving, with minimal error, and our and it showed two methods of strain method and displacement method, and how both of those methods produced um, you know, similar results, which show that they were both reliable. And the foam calibration that we did in the beginning shows proper ways of strain measurement, and it shows that we had correct wiring before we actually did our experiment. And the deflection we got going, of the bending going up showed that it matched our predicted values of what we're expecting for this experiment. So the pattern was correct. So everything in regards to our stress and strain um, and our force versus displacement, as well as our deflection, matched what we're expecting for the experimental data. And for conclusion and lab takeaways, the Flexure testing, it properly demonstrated 3-point bending, or bending in general, and how stress and strain is seen in bending. It led us to accurate measurements of our Young's modulus for the polycarbonate acrylic material sample in both the displacement and strain gauge methods. So again, it shows that we can use either of these to get measurements. And the linear relationships of the graphs, it indicated how the acrylic responded. Again, the elasticity, which showed that. Some takeaways we took from this are that how we zeroed out the measurement equipment and used the equipment to influence the accuracy of our data. So basically how us zeroing out, how us using the equipment actually impacts how our data will come out. So our accuracy was, again, very good. So that shows that we followed the proper steps in using the equipment. And a result of that is that our Young's modulus that we have is consistent with the actual Young's modulus of the material. So that showed that our setup and data collection was accurate. The experiment reinforces the link between deflection, load, and stiffness, which is seen across the real world. So it showed that those three things are aligned together. And you can see this in the real world, like with bridges, aircraft structures, and more, right? Because all of these things have to be taken into account, whether it's, in terms of what it's going to be used for. For future work and recommendation, it was just making sure that we're pre-checking our clamps and strain gauge before proceeding. So just making sure all of our materials are properly set up. And one of the biggest things is just making sure that the acrylic gel is put on properly and the glue is set up properly, as you can see in the image here, and making sure voltage readings are properly set up, because for this experiment we had to be careful with the voltage reading, so we had to clamp that twice so that we get proper voltage measurements, because that would impact our results. For references, we got some references from our lab handout and from Values for Common Materials, the website, and MatWeb in regards to the actual Young's modulus of polycarbonate acrylic that we needed, and more. Thank you.